Funding for the Gone Fission Nuclear Report is provided by the Energy Communities Alliance.
Welcome to the Gone Fission Nuclear Report, your one-stop source for all the latest news from the Department of Energy's Environmental Management Program. Now, here's your host, Michael Butler.
Hello, and welcome to the Gone Fission Nuclear Report. Today is Monday, May 20th, 2024. We're covering all the news from the Department of Energy's Environmental Management Program across the country. And we thank our friends at the Energy Communities Alliance for being presenting sponsor for today's episode. ECA, Local Concerns, National Impact. If you haven't subscribed to the Gone Fission Nuclear Report, we invite you to do that now. The Department of Energy's Environmental Cleanup Program is more than tearing down aging, contaminated buildings. In this week's episode, we'll take a look at another dimension of cleanup. I'm talking about the conversion of depleted uranium hexafluoride, or UF6, at Paducah, Kentucky, and Portsmouth, Ohio. Depleted UF6 is a byproduct of the uranium enrichment process. Two specially designed plants at Paducah and Portsmouth are converting depleted UF6 contained in over 63,000 cylinders into a more stable uranium oxide form for reuse or disposal. The cylinders occupy acres of land at the two sites, land that may one day be reused for new job-creating government or private sector projects. A byproduct of the conversion process is hydrofluoric acid, which has wide applications in industry, from pharmaceuticals and refrigerants to aluminum, plastics, electrical components, and more. Hydrofluoric acid from the conversion process is sold to industry and is a revenue generator for the federal government. Resulting funds are used to offset operational costs in the cleanup program. It is one of the few moneymakers in a cleanup program with billions of dollars in costs. In today's episode, we'll learn more about the depleted UF6 conversion program. Our guest is Zak LaFontaine, DOE Program Director for the Depleted Uranium Hexafluoride Conversion Program at Paducah and Portsmouth. We're talking now with Zak LaFontaine. Zak is the DOE Program Manager for the depleted uranium hexafluoride plants at Paducah and Portsmouth. And welcome to the podcast, Zak.
Hey, thank you. I'm happy to be here.
Well, we're very glad to have you to talk about this topic today. I'd like to start with the basics, if we can. Some people may not be familiar with depleted uranium hexafluoride, and I'd like to start, if we can, just by talking about what it is. What is depleted UF6, and where does it come from?
Yeah, so depleted UF6 that we're processing at our facilities is a result of years of gaseous diffusion plant operations. So at Portsmouth and Paducah, as well as Oak Ridge, they were gaseous diffusion plants that were built in the 1950s that operated until 2001 at Portsmouth, and then the mid-2010s at Paducah. And through a result of that process, you take natural uranium, which is 99.3% U-238 and only 0.7% U-235, which is the isotope that we're really interested in from an enrichment standpoint. And you take it, and through gaseous diffusion, you run it through essentially a bunch of filters to concentrate that U-235 isotope. As a result of that, you create a lot of depleted UF6, which is almost a 9-to-1 ratio as far as depleted to enriched, in terms of mass. So throughout the production at both of these facilities, we amassed a large number of cylinders of depleted UF6, and these cylinders are 12 foot long, 48 inches in diameter, and about 14 tons in weight, full of depleted uranium hexafluoride, which is a solid at room temperature. And that UF6 compound was selected for the fuel cycle because it's, I'll put in air quotes, an easy compound to separate, later on in the fuel cycle, as well as it's selected due to its properties. So it's at the ambient room temperature, which makes it convenient for storage and movement. And then it has a relatively low triple point whenever you're heating it to volatilize it, for a gaseous state for future operations. So that's kind of why we have UF6. Now, where it comes from originally, when you find uranium out in the wild, you do have to go through a process it's actually a conversion process to create the UF6. And a lot of that came from the Honeywell Metropolis facility. It's in Illinois. So that's the majority where our UF6 started. And then throughout the years of GDP operation, resulted in the depleted UF6 that we're taking care of today.
So just to maybe restate and be clear, the depleted UF6 has a larger concentration of U-238 and very little of the fissionable part of U-235, correct?
Correct. Yeah, nominally anything the depleted is less than 0.7% assay, which is the U-235 component.
Okay. Well, this is a conversion program, and you're converting the depleted UF6 into a uranium oxide. And why do you need to do that? Why can't you store it or dispose of it just as it is?
So there's a couple of reasons. One, the DUF6 is, like I said, it is a solid at room temperature, but it's very reactive with moisture in the air. So even though we've got it in all these thousands of steel cylinders, if there's any air and leakage over time or any reaction with air, that volatilizes. So you have a UF6 reaction, and it reacts with moisture in the air, creates HS vapor, hydrofluoric acid, which is a highly acidic, very corrosive compound, and it's really the most hazardous chemical in our facilities, as they are. So from a storage standpoint, the cylinders aren't, it's forever home. Is one way to think of it. It was convenient for, GDP operations. And so, like I said, we amassed this inventory. And then the other big reason is there's a public law that was enacted in 1998 that directed DOE to come up with a plan to disposition this material at both sites and to construct the DUF6 facilities. So that public law, in conjunction with the USEC Privatization Act, is really what kicked off my project and getting these conversion plants built and started up to disposition that legacy left from the former enrichment facilities.
So the hydrofluoric acid really is created during the storage process. Is that right? Just by virtue of the fact that the UF6 is exposed to the temperatures, it's created as part of just being in normal storage. Is that right?
Not ideally. So whenever they first filled these cylinders back in the 50s, 70s, 80s, 90s, that cylinder was pulled down to a vacuum. So there was it was inert and there was no air in there. The concern is that over time, with expansion, contraction, if you have any cylinder, all these cylinders have a valve on them. So we have to go out and maintain all the valves. If you had any air and leakage through one of those pathways, that would react and generate UF or HF inside the cylinder itself. Plant.
Okay, well, very good. The conversion process also creates a sort of a beneficial side product called hydrogen fluoride that's used by industry. Can you tell us about that?
Yeah, so like I said, the HF that we produce in our facilities is reclaimed, and it's used in a lot of applications, such as pharmaceuticals, refrigerants, plastics. One of the more interesting and kind of emerging uses for it is its use in electrical components and even EV batteries. So it's used in some production of lithium-ion batteries, and it's also used to etch glass as well as etch silicon for circuit boards and that kind of thing. So it's kind of an interesting time on the UF6 side. We've got our inventory is becoming more attractive just because of the kind of the geopolitical environment we're in. And then also our HF product that we make on the back end is becoming more attractive due to the kind of electric vehicle and energy renaissance we're going through. So it's an interesting project.
Mm-hmm. Well, how hydrogen fluoride get from the DOE conversion process into the hands of industry so they can use it? What's the process, the route for that?
So we've had an industry partner since the inception of the project, and they actually handle all the transportation for us as far as all the rail cars, tanker trucks. They take care of that fleet and then take care of all the logistics of getting those rail cars or tanker trucks to our facility. And then we essentially load it onto those facilities with our own USW operators, United Steelworkers operators. And once it leaves our site, it's directly into commerce.
So is hydrogen fluoride, is it sold to industry by DOE and your contractor and actually a moneymaker for the government?
It is. So we do recoup a small portion of our operating costs from the sales there. So it is essentially a recycle type of process when you zoom out.
Okay. Well, this conversion process is a rather massive undertaking. You've got a big job on your hands there. There are more than 63,000 cylinders, as I understand it, of depleted UF6 that are stored in the cylinder yards at Paducah and Portsmouth, and the total is something like 800,000 metric tons. So there's a lot of it. Let's talk about what's involved in this project, both in terms of the quantities that we just mentioned and also the time frame. This is a decades-long project, this conversion to the more stable form. Is that correct?
That's correct. Yeah, so we do have decades worth of work at both sites. So it requires a few things. Like I said, there is a large number of inventory of cylinders that we have to go out and perform surveillance and maintenance on. So what that looks like is that we have folks go out and individually inspect the cylinders, make sure there's nothing awry with them. And we also do ultrasonic thickness testing, reading of the cylinders themselves to make sure we're not seeing any corrosion or anything to that nature. And then from a long-term planning standpoint, a lot of it is figuring out what we can do to improve the plant operations, improve uptime, and then improve throughput. So, we've recently done quite a few plant modifications, and we've been focused primarily on the support systems to the facility itself and trying to get rid of single-point failures. So that's been a big focus, and now we're starting to turn the dial a little bit on the individual process modifications we can do inside the plant. And then, another big hurdle we're getting ready to jump over is just the long-term oxide shipping. So right now for the project to date, after we convert a cylinder and put it, UF6 cylinder then becomes an oxide cylinder, they're primarily stored back out in our cylinder yards. We have embarked on a few shipping campaigns, but by and large, we're right now storing the cylinders and creating kind of a backlog that we will need to tackle in the next few years to wrap up the entire mission.
Well, during the COVID period, you went through a series of upgrades at these facilities to make your operations both safer and more efficient. Can you tell us about those upgrades?
Yeah, absolutely. So a number of our modifications were, kind of the genesis of them was worker feedback. So, the folks out running the plant generally know best where we can improve. So I'll kind of walk through a few of those first and then get into some of the more process-related ones. But let's see, the PVC to stainless mod was a big one for us. So as I mentioned, we have potassium hydroxide, KOH, is used in our facility to neutralize the remaining heels. So like I said, after you're done processing a cylinder, there's about 50 pounds of UF6 that's non-volatile. So we inject potassium hydroxide in there to make it safe to be able to do the cutting and welding to turn a UF6 cylinder into an oxide cylinder. And then we also use it in our scrubber systems throughout the plant as well. So we scrub any off gas from that HF stream that comes out of the top of our conversion units with potassium hydroxide before it can safely go through our HEPA and our stack. As a result of that, we have a lot of pipe with potassium hydroxide in it, and the original construction material was PVC plastic for that piping, which is a suitable material of construction, but these plants were built in the 2010, 2011 timeframe as far as when we first were put into operation, and we were starting to see that piping become brittle, cracking, and that is a very caustic solution that we definitely want to control from a hazard standpoint. So we went through and replaced that at all the sites from PVC to stainless steel, and that's been a big benefit for us and was driven by worker feedback. And actually at Portsmouth it was implemented, and as well as some portions at Paducah were implemented by our United Steelworkers themselves. So welding stainless steel is definitely not a simple task, and they did a great job on that one. Another big one that we did during COVID was we increased the HVAC in one of our more higher temperature work environments. So we have an area where our filter vessels are. So as we're moving oxide throughout the conversion facility, the air pneumatic system for that goes through a series of filter vessels, and the room that houses those vessels gets pretty warm, in the excess of 90 degrees Fahrenheit. So we installed, essentially a large air conditioner to make that more amenable to work activities, and we also installed permanent platforms that were formerly had in place kind of scaffolding type, not a temporary configuration that had been there for too long. So that was a big one. That was worker requested and implemented at both sites. And then getting into some of the more processing oriented, I mentioned, briefly a minute ago that we were in the process of getting rid of single point failures. So probably the biggest modification that we did is that we installed a bulk hydrogen system. So I mentioned that second reactor in our conversion unit requires hydrogen as well as steam. So that hydrogen previously was a single point failure. We have hydrogen generators at each site that essentially takes natural gas and strips the carbon off of it to generate pure hydrogen. And if that hydrogen plant went down, our whole plant went down, all the processing lines. So installing this bulk hydrogen system was pretty great because it allows us to pressure up essentially a day tank with hydrogen generated from that on-site system. And we could also bring in tube trucks from semi-trailers to facilitate and run plant operations. And since we put that in service in about December of 2021, we've had 250 days between the site that we're able to operate, but we would not have otherwise. So, better part of a year, just in that short period of time. So we've already kind of returned our investment on that about 6 or 7 times. Couple more. Another big one we did was we have, as I mentioned, we store aqueous HF at the site. So we've got large 10,000 gallon tanks that we use for the load out onto tanker trucks or rail cars. Those have a common vent header, and also the piping going into them was never outfitted with isolation valves originally. So if you had an issue on one tank, you had to shut the whole plant down. It was kind of another single point failure. So we added a double block and bleed isolation for all those individual tanks as well as the vent line. And then the last one I'll mention would be our redundant air compressor. So we did have 2 air compressors at the site. However, due to operations, we have to have air to operate and be able to safely operate. So we did have to routinely have one in lead, one in lag, and if we had one down for maintenance, you're sitting again on a single point failure. So we've installed a third redundant air compressor that's actually larger than either of its 2 predecessors, about 140% more capacity, which is also a benefit because it's a little more oversized than what we had originally, which has been expanded upon by other plant modifications. So that's been another big one that's been able to carry the load of the plant when the others were down.
Well, you mentioned United Steelworkers and the role they played in providing some worker feedback into these improvements. DOE there and other parts of the country does most of its work through contractors, and you have Mid-America Conversion Services there as your prime contractor, and along with the United Steelworkers being part of that. Can you tell us a little bit more about the involvement of the contractors and the role that the contractor plays and the union plays and the success of the work that you're doing there?
Yeah, absolutely. So our contractor, Mid-America Conversion Services, has about 490 employees. It varies a little bit. But that we do have one single contractor that operates both facilities. And they also have an office in Lexington, just like our PPPO office in Lexington, where a lot of their business management folks reside, project controls, and that kind of thing. So what that looks like at the sites, we have a little over 200 folks at each individual site, and then we have about 50 to 60 people in Lexington. Of that, the total 490, 240 or so of our workers, so about half the workforce, is our USW United Steelworkers employees. So that's out of USW 689 at Portsmouth and USW 550 down in Paducah. And these folks are the ones that do the majority of the hands-on work at the facility. So these are our operators, our maintenance mechanics, instrument technicians, electricians, our site services tech, all of our health and safety technicians. And as I mentioned, their experience is invaluable. A lot of them generally come from either other chemical plants that are local or have experience at the GDPs. Probably more so at Paducah since they were operating a little sooner, but we do have a few folks at Portsmouth that operate the GDPs up here as well. What having the one single contractor also does, and has been a big benefit recently, is it allows us to share lessons learned. So a lot of modifications that we do, workers will want at one site, and we can implement it at one site, talk about how it worked, and even send folks. Most recently, we sent some folks from Paducah to Portsmouth and vice versa, some supervisors as well as operators to just see how the other plant operates. We have, our process is fairly well known. I mentioned the kind of the rudimentary chemical part of it, but there are processing parameters that can the operators kind of have swim lanes they can stay in, and it's pretty interesting to hear how one plant will operate versus the others, because even small percentages and flow can change a lot of things. And we also have an integrated project priority list that we've implemented at both the sites, and that is filled with worker feedback. So any kind of plant mods that come up during our safety meetings, that kind of thing, or just anyone's free to bring them up anytime. There's a list that's visible to all, and we can kind of work those off as we go through. So it's a very good relationship, and like I said, we definitely need them to operate. It's 100%.
Right. What is the ultimate disposal plan for the depleted UF6 once the conversion is complete?
So I mentioned the cylinders, after they come out of our facility, so the oxide that's created in our conversion unit then goes back into a modified UF6 cylinder with a flange on it. They're principally stored back out in our cylinder yards at the current time. We do have an SEIS, a Supplemental Environmental Impact Statement, and a Record of Decision that allows for 3 different disposal pathways. It was issued in, I think it was 2020. So that allows us to ship this material to either WCS out in Texas, Energy Solutions in Utah, or NSS in Nevada. So if beneficial reuse is not realized for the inventory, that's generally the spots where we'll go. But there are a lot of beneficial reuse opportunities. We've been kind of exploring that, and there's more on it in the news every day. So I'm still hopeful that we'll see some beneficial reuse for some of this material as we proceed through the project.
What form would that take? What does beneficial reuse look like with this material?
So the U3O8, from a DOE standpoint, probably the most readily available form would be any kind of downblending that's needed. Having the depleted UF6 just from a mass averaging standpoint is beneficial. There's also metal production is another thing we've been looking at. High purity depleted uranium metal can be produced from either the UF6 or the U3O8 on the back end. So that's another. Those are the 2 kind of biggest ones that I see.
Mm-hmm. Zach, when most people think about the EM cleanup program, you think about the big buildings, just like your gaseous diffusion facilities, they're being torn down, and that's the scale of the cleanup that most people have in mind. This depleted UF6 is a different thing entirely. It's important in terms of the overall EM cleanup effort. Can you tell us? It's different though. Can you tell us how it fits into EM's overall missions and priorities?
Yeah, so absolutely. So I mentioned, kind of the genesis of the project was the public law that enacted, but it really at a fundamental level, it's to clean up the. You see the large buildings, but what's not as easy to see are the thousands of UF6 cylinders, sitting out in the yard as well. So, the grand vision for, especially here at Portsmouth and where we're a little further along, is to be able to, systematically go back and transfer land back to the community so we can reindustrialize the site. So to do that, we need to get rid of, all this legacy liability essentially that we have on hand. And I think it has a really important part to the fuel cycle at whole too. So that public law that was enacted that, stood up our facilities also requires for us to be able to take any commercial depleted UF6 as well. So we do have to be able to provide, on a cost reimbursement standpoint, a quote for what it would take to disposition their material as well. So these facilities are kind of uniquely poised, just as part of the fuel cycle and especially part of this nuclear renaissance, to be a pathway for dispositioning kind of the back half of the fuel cycle. And just from a overall risk reduction standpoint as well, the UF6 cylinders that we have are one of our larger source terms for any consequences either on site or off site. So it's in everybody's best interest that we can process those responsibly and work through the material so we can, like I said, give the land back when we're done and do something really cool with it with the community. Mm-hmm. That's the overall goal. And it is a pretty neat selling point just for workforce as well, because like you said, I love it when I give tours. If you're into construction projects, we've got a lot of big ones of those that we can interest you with. But we've also have if you're more into operations, 24/7 operations, troubleshooting, and implementing plant modifications and improvements, then I think we've got you covered here at the UF6 project.
Well, Zak LaFontaine, the DOE Program Manager for the depleted uranium hexafluoride plants at Paducah and Portsmouth, thank you very much for joining us today on the podcast. We appreciate your time and the information you provided, and we're happy to have you with us.
Hey, no problem. Thanks for having me. Enjoyed the conversation.
Funding for the Gone Fission Nuclear Report is provided by the Energy Communities Alliance.